Excellent. So waiting for a second. Yes, we are live. Perfect. Going to start. Welcome once more to .NET Zurich event. Today is March the 4th, and the images we are using are provided by starwars.com, free to use, hopefully also free of copyright infringements. Otherwise, the videos will be put down. So crossing fingers there. Today, I'll put these and step back.
Also, your sound is still not working.
No. I did not put sound because we had these taken away once because we were using music. So I had the background. So in fact, we did even at the office with real music. But yeah, I did not want to put it in purpose. Also, reading this is kind of hard, so I let it away in purpose. Sorry about that. But you can put the music yourself, like tan 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 tan. Don't make me sing ever. So welcome to our performance day. It's pretty cool, but first I'd like to give thanks to our gold sponsors, Offering Solutions, BBVAU, and for Texture, as always, and to our location back when we were able to have a location, Impact Hub and Stanford Group, and of course to our partners, Azure Zurich User Group, .NET Central. Hi, Daniel, which we have one representative here today. We have as well .NET Day Switzerland and Swiss Angular. Thank you so much for having us. Today in the stage, we will have Daniel Marbach. He's an engineer and solution architect at Particular Software. He's a Microsoft MVP, speaker, open source lover. Here you have his Twitter ID, his LinkedIn handle, and his GitHub as well, which has the name of his name. Daniel Marbach. He's basically, to me, somebody that opened the world of .NET when I arrived in Switzerland. He's basically a smile, always friendly, technology and fitness lover, a public speaker, also a good coach on public speaking, also a good user group leader. He's, when I came and was looking for a local user group here in Switzerland, he helped me and a friend to set up the Zurich.NET user group. So we owe him that. He's always loving to share and create things with his brain and put them in GitHub. So thanks for that again. And yeah, and he's also always sharing his insights, providing useful feedback. Thank you, Daniel. And that's it. The stage is yours.
Thank you very much, Jose. Now you put me on pressure here on the spot, I guess, with what you said with that awesome introduction. Now I'm peeing my pants right now to
you deserve it, man.
Yeah, I can start sharing my screen.
Please do.
Yep. Yes. Just see. Here we go. Can you all see my screen?
We see it.
Perfect. Let me just see. I'll put your pretty faces over here so that I can still see you. I will also be monitoring the chat a little bit. So if you have any questions, Jose, I assume you will be monitoring the YouTube chat area. I guess if there are anything on YouTube or on the live stream, I can also answer those questions. And yeah, thank you very much for the nice introduction. And tonight we're going to do, well, it's a performance day, but it's already night, right? So tonight we're going to basically learn some of the things that I have personally learned, like performance tricks from contributing to the Azure SDK. So one of the things that I do as a person is that unfortunately, I cannot just read a book and then feel like, oh, I'm going to use that in production or tweak some code, because usually it doesn't really stick to my brain. So that means I have to essentially pay with blood and sweat to go through the things and actually learn it. It's sometimes time consuming, but it's also very rewarding when you can see that the things that you actually did are put in place and end up somewhere. And then I usually try to condense those things, those learning experience, into a talk, because I think, or at least the perception of what I have, is that potentially many people go through this process of try and error and trying to find out how things work. And especially the performance side of things, it's a huge area with very different levels of things you can do and you can learn from. And I want to share some of the things that I did. You can reach out to me on at Daniel Marbach on Twitter, or if you have any questions, of course you can ask it in right now in the chat, or during the talk in the chat, or at the end of the talk. But you can also send me an email to daniel.marbach@openplace.net if you have any questions. So let's get started with the conversation here. So I want to set the details straight. So in this talk, I'm not going to essentially talk about things like vertical scaling, horizontal scaling, and stuff like that. So this talk is purely and primarily focused on performance optimizations that can be done in the code. And especially C# and .NET. I will be showing C# and .NET code. Of course, some of those things you can also achieve with F# and other languages on the .NET runtime. Because I primarily do C#, I will show the things in C#. But there are also plenty of good guidance around in the web. For example, if you're a F# lover, to apply some of these techniques to F# as well. And I believe that there is a lot of evidence out there that the .NET platform itself, as well as the language, has been evolving over the past few years to a very modern and high performance platform. So nowadays it's rarely ever needed to really go, if you're in the .NET space, to really go to C, C++, right? It's less and less needed to essentially achieve code that performs very well at scale. And as a matter of fact, many of the things that are still today in the .NET runtime that are sometimes still C, C++, they're actually getting moved more and more over time into managed code, because having managed code has a lot of benefits if you do it right. And with modern additions that have come in the C#7 timeframe and things like span and memory that we're also going to talk about here, you have actually a lot of ways you can now, within the safety net of the language and the runtime with managed code, to actually write code that performs very well. One of the things that I usually hear is when I talk about performance, or when I show some performance optimizations that I do to my colleagues, I usually hear that, well, but that's crazy. That's just premature optimizations, right? Why would you even bother to do this type of stuff? And I'm going to show you a few techniques that can sometimes be called out esoteric. But I want to make sure that you just don't blindly jump to conclusion and try to apply these techniques everywhere, because that would be very wrong. And that's not the message that I'm giving in this talk. My message is essentially that performance optimizations, they matter when the code that you're tweaking is executed under scale. Because what happens is they make your code more efficient in terms of resource usage, execution time, throughput, and memory usage. And I know that personally, I've been suffering from that too. Performance improvements can be very addictive. But what's also true is that nobody really likes to optimize code that is fast enough or is only executed once a day, right? But what does scale, or what does code that is executed under scale actually mean? And how can we find out whether the optimizations that we are trying to write actually have value, and that we are not getting called out as premature optimizers, like Sergio just said in the chat. And that is one of the goals of this talk as well. I love this quote. It's from David Fowler, where essentially from his talk, the talk is called At Scale Implementation Details Matter. By the way, I'll also have the talk link to his excellent talk in the slide notes on GitHub if you're interested to watch that. So he says that at scale for an application can mean the number of users that will concurrently connect to the application at any given time, the amount of input to process, or the number of times data needs to be processed. And I think the most important part is the next paragraph, where he says, for us as engineers, it means we have to know what to ignore and knowing what to pay close attention to. And I think that's the key. That's the essence of actually doing a good performance optimizations. So what we have to do is essentially, when we look at a piece of code that is in place, we have to basically look at the assumptions and try to discover the assumptions that have accumulated over time in the given code base. We have to pay close attention to how things are instantiated, how things are parsed, processed, for example, per request. And then we have to understand or try to resurrect how those assumptions in the code base actually affect the performance characteristics in terms of memory, throughput at scale, right? So, but of course, that's all a bit fluffy that I just said, right? Because it's we as developers, we actually love to have rules or best practices that we can just blindly apply. And of course, I'm also bringing you some of these rules that I've extracted from my experience of doing performance optimizations. And give them to me. And to say it with the voice of Boris from GoldenEye James Bond, right? We want to have the code to do performance optimizations. And basically, the general rules of thumb are these two, right? That's it. Well, now we can go home. It's like avoid excessive allocations to reduce the garbage collection overhead and avoid unnecessary copying of memory. That's the rules of thumbs that we have to think about. But then if we dive deeper, we can actually find some really good rules underneath these categories that we have to take into account. So the first one is, if you look at code, be aware of closure allocations. And I will go into depth about these topics. So I'm just going to fly them over. Then be aware of parameter overloads of methods. Then where possible and feasible, use value types, but pay attention to unnecessary boxing if you use value types. Then that one is probably the most contradictory and sometimes called out as esoteric, but think at least twice before using link queue or unnecessary enumeration on the hot path. Pool and reuse buffers. And then for smaller local buffers, consider using the stack allocating stuff. And then for the unnecessary copying of memory, watch out for immutable read-only data that is copied unnecessarily. And then look for stream and byte array usages that are copied or manipulated without using span or memory. And then the next one is replace existing data manipulation methods with newer span or memory-based variants. So these are basically the things. If you now fall asleep during my talk, these are the things that you have to remember, and you can just take a screenshot and enjoy the rest of the talk, because we are now going into like the depth of these topics that we are trying to cover. First of all, the topic of avoid excessive allocations to reduce the garbage collection overhead, and the link queue part, right? Think at least twice before using link queue. I mean, don't get me wrong, link queue is great, and I wouldn't want to miss it at all. I think it's a great addition to the runtime and to the language. Yet on the hot path, it's far too easy to get into troubles with link queue, unfortunately, because it has a lot of hidden allocations. It's difficult for the JIT to optimize. And let's look at a piece of code that is coming from the .NET Azure SDK. The class is called the MQP receiver, and the MQP receiver is essentially the driver behind Service Bus, Azure Service Bus, and the Event Hub to receive messages essentially from the cloud. So this is the piece of code. Of course, I cut away a lot of stuff to just make it very simple for this talk. This is the MQP receiver. It has a concurrent back that is called locked messages. And the most important method is this one here. It's called complete internal async. It accepts an I enumerable, because the SDK guidelines say that you have to accept the broadest applicable enumerable type, not actually lists or stuff, but the broadest one is I enumerable of strings, and block tokens are essentially GUIDs, but they're represented as strings. And then what the code did at the time was it essentially did a select, turned those strings into GUIDs, and then called to array. And then it also did check whether it has already seen this lock token before, because it's a stateful entity that actually manages different lock tokens from different messages. It actually does an any. And then based on that, it goes in one path or it goes into the other path in the code. So essentially controlling the flow, whether it has already seen in that concurrent back that GUID. If we decompile this code, it looks more or less like this, right? So we have a bunch of compiler-generated garbage that nobody can really understand, but really doesn't have to really understand, right? But we have this piece of the puzzle here. So the complete internal async method, it creates, if we pay close attention on line 8 and 9, we see that there is this function delegate that it creates, but actually it's a cached function delegate because it's assigned to a static field. So we don't have to worry about that. Then let's look at the next one. Then we have a new function delegate of type GUID and bool that points to the complete internal async b underscore blah, blah, blah method. And that one is actually allocated every time we call complete internal async. So that code is called under scale, under heavy load. So we will potentially be completing thousands and thousands of messages a second. And therefore, every time we call this method, we will be allocating a new function delegate. It's possible to get rid of this problem pretty easily. So we can turn essentially this thing into a for each loop, right? So what we do is we have, instead of the any link queue method, we now have a for each for the token GUID. We go through there, and then we have an if, and then we just say contains. Is contained in this one. And if we compile this down or decompile it, we can see this is what the compiler generates. And if we look a bit closer, we can see now that we have now everything is cached, right? So we have now a compiler generated field that is this C9 __ 2, blah, blah. And we have a new func string of GUID that points to complete internal async. And there is no allocation anymore of the new func of GUID. So there's a question from Sergio. Can't use static anonymous functions. That's also a possibility. You can sometimes use static anonymous functions. There are certain cases where you can optimize code as well to do that. That's absolutely true. This was just the simplest way to go about it, to just turn essentially the link queue any into for each loop. But of course, we can only actually know whether the things that we are doing have any positive side effects if we actually measure what we have been doing. And I regularly use benchmark.net. It's an amazing tool, and it generates nifty output. This talk is not going to be about benchmark.net, so I will just show you some of the results. And by the way, I know it's a bit overwhelming, so don't really worry too much about this slide on the details, because I'm just presenting you the data that you can see that I actually have measured what the improvements are, but I'm going to summarize it for you. And what we essentially have here on this slide is that by just getting rid of the any, we were able to squeeze some really good performance improvements out of it. So we actually have a speed improvement of 20 to 40%, depending on the collection type that we're passing to this method. And we have a garbage collection, a chain 0 garbage collection, reducing of 20 to 40%, depending on the use case. And for like the empty collection case, we have for arrays, for example, even no GC overhead anymore. So which is great, right? But just basically turning the any into for each, we got this amazing results. But sometimes though, we can do even more. For example, there are a few general rules of thumbs that we can follow when we refactor code from link queue to more collection-based operations. And as Boris would say,
Give me the cores, Italia! Give them to me!
Of course, I have again a few rules for you. So when we look at refactorings, where we turn essentially link queue to collection, link queue based operation to collection based operations, we can say for representation of empty arrays, you should always be using array.empty. Then, for example, for representation of empty enumerables, you should always be using enumerable.empty. Then one key factor of improving the speed is you should prevent collections from growing. Many times we forget it, that when you create a new list, for example, it has a number of slots allocated to it. And once you start adding stuff to it, at some point it starts growing its internal internal arrays, and then it needs to reshuffle stuff and resize arrays, and these are really expensive operations that take a lot of time but also allocate. And then the next thing is also you should always, if you can, essentially be using concrete collection types. So if it's usually better that in the internals of your code to design the code path to not, for example, accept IEnumerable or IReadOnly collection, these type of interfaces, but actually directly the array or the list. Then you all have also less allocations because then it can be optimized to directly use the struct-based enumerator that is returned by these collections. Otherwise, you will have overhead again. Then one of the things that's also quite handy with the introduction of the pattern matching features in C#, what you sometimes can do is when you get more generic collection types, but you know that for the majority of the cases, you're getting past a certain type of collection. You can, for example, leverage pattern matching to essentially cast a collection into a specific type so that you get the count. And then you can use the count to essentially figure out how large it is and allocate dedicated collections of a certain size to prevent essentially things from growing. Or with the newest additions in .NET 6, we also have enumerable.tryGet non-enumerated count that basically takes care of getting the count from an enumerable without actually iterating through all the elements to improve the speed. Good. Let's have a look at how we can apply those principles that we just had a look at to the previously seen code example. So here we still have, even though we turned the any, right, we turned it into for each, we still have this lock tokens.select, and then we turn it into a GUID, and then we do two array. One of the things that was clear from the telemetry that the Azure .NET SDK team had, and that came out in discussions on the pull request that I did, was that most of the time, even though we are accepting an IEnumerable, most of the time users are actually passing a concrete list or an array into it. Only really for testing, people are passing a lazy enumerable. And we can leverage that essentially to optimize this code, this knowledge. So what we did then was to essentially write to write a pattern match here, because they cannot target yet .NET 6. They're they have to be net standard compliant, so we have to use pattern matching here. So we cannot use enumerable try-get non-enumerating count. So what we do is we actually look at, well, is the collection that we are getting passed, is it of type IReadOnly collection of string? And then we take it. Otherwise, we essentially do lock tokens to our array. So we materialize the list. And then we switched the internal representation of the method. We switch it to our read-only collection of string. It's still not entirely perfect, right? Because like I said before in the general rules of thumb, we should be accepting concrete lists and stuff, but it's still better than what we had before. So we accept that. And because we now have a read-only collection that has a count or a length that we can actually access, what we can do is we can actually go and say, okay, we create an array, we initialize it with the specific count, or in the case where we have nothing, we use the array.empty as I've shown you in the best practices. Of course, with the array, it's not that important to really initialize it with a count. It would be much more important with a list, but I'm using here this to illustrate because that was the code that we had in place, right? And then what we do is, instead of doing the select and everything, I'm creating a new GUID, and then I just use the array indexer to assign the token GUID, and the rest is all the same, right? So if we measure this, and pump it through different collection types, we can actually see that in many cases, and we actually did do another improvement, right? So we have like 5 to 64% improvement and 23 to 61% garbage collection reduction. But, and that's the thing, for some cases, we actually made it worse with this optimization. So for example, if the majority of the cases we will be passed to this method lazy enumerable that are lazy enumerated, then we're actually doing a bad job with this optimization. So is that an indication that we shouldn't be doing such a refactoring? Well, the answer is it depends. Well, right? So the key here is, again, is the context, like David Fowler said, right? The context of this piece of code. So we need to understand it, how it's going to be used, right? And if we know that in the majority of the cases, we're going to get past already materialized collections, then we have made significant improvements, but we made the code a bit more complex, right? But if we know that the majority of the cases we're getting essentially lazy enumerables and stuff like that, then my personal preference would always be to go and say, well, readability should be the key driver instead of essentially gold plating every part of the code base, right? And there are likely other areas in your code that are slowing things down more. So you should essentially go and fire up your memory and performance profiler, get a better understanding of the areas of the code base, and then optimize those first. And only once you have done that, and you know that it's actually doable, go back to these types of optimizations, right? So sometimes it's, sorry, yeah, Jose?
Do you want to take questions as they come? Because you have like a couple on the chat.
I can, yeah, sure.
All right.
Should I read it, or? One I saw it. One is just a comment. It's not really a question. So the question was: I often use helpers like the following. Is it good approach public static, I read only collection as read only collection, and then essentially casting the read only collection? Helper methods like that are similar to the pattern matching approach. Absolutely. But again, if you, for example, have .NET 6, you can use enumerable.try get non-enumerating count in areas where you actually need to get the count. But yeah, sometimes you can actually change your code to not accept enumerables and actually stick to that if performance really matters, right? But of course, you have to make trade-offs because, for example, with the Azure SDK, the public methods are going to be exposed to a lot of users, right? And therefore you want to be as broadly applicable as you can from an API service perspective. And then you need to make trade-offs. If it's just your library that is executed under scale and is not exposed to many users or customers, then you might go and say, you know what, we just directly pass on lists and stuff, and we know it might be mutated, and we deal with all these consequences, but we have proof that it's actually faster to do it that way. Again, like with all the things, like I've shown also here, it's important to look at the given code path, understand how it's going to be used, and then make the optimizations if it actually is useful to do it. And sometimes it's not, right? Okay. Then be aware of the closure allocations. I have already touched on this piece on closure allocations, essentially in the first introduction when I talked about switching from any to for each, because that actually got rid of a closure allocations. But essentially closure allocations, they can happen anywhere where you have lambdas, for example, action delegates, function delegates that are essentially invoked and that capture context that is outside that lambda. Let me give you an example. So the Azure Service Bus SDK has internally a helper method that is called run operation. And what it does, it's essentially like poly. It essentially executes a method in a while loop. And if, for example, the server is busy, it needs retries, it just executes the same operation up to a certain threshold over and over again, and it uses delays to essentially wait a little bit and then try again. So that's all what this method does. And the method looks like this. It's called run operation. It accepts a function delegate that gets a time span in, returns a task, and then it executes the operation, passing on the timeout to that operation and has a while loop surrounding it. So pretty simple, right? The usage looks like this. So, for example, some piece of code will essentially call an internal method, create message batch internal async inside the SDK. It then gets a result back, assigns it to a local field called message batch, and then it also passes in the options. So what this code essentially does, it captures as a closure, it captures the message batch variable that we have here on the slide, as well as the options. And if we decompile this code, this is how it looks like. So essentially, what we have is we have a new display class allocation for every execution of this code, and also a new function delegate allocation that passes in a time span and a task for every execution of this code. And that is unnecessary pressure on the GC, and we can do some really small improvements to make this code even better. So what we do is, first of all, when I did these changes, I looked at the context of these things, and many of the methods that were called inside the run operation method already were switched to using value task, right? And value task is basically almost like a discriminated union of a task or an actual value. And it's very useful if you have cases where, for example, when you call it 10 times, 9 out of 10 times, it's going to return synchronously a value. And only once it actually yields and fetches and does some IO bound operations, then value task is a perfect use case. So, and in order to support that, to not allocate for APIs that have value task, we can also return a value task here. And then I accept an input parameter, T1. And now what I do is essentially I switch the delegate to get not just the time span, but also that input parameter as a generic argument, and also pass that input parameter to that method. And that is basically the state that we use to capture, but we pass it into the method, and then the method passes that to the operation itself. And that is the trick. And with that trick, we can essentially build on top of this generic method various functions that return results, but we can also build upon with the action delegate cases where we don't actually return something, but we just execute code that doesn't return anything, just with this pretty simple functional changes that we did. So that's how the operation looks like. So we then build upon this helper function run operation. We create the one that doesn't return any result. So again, we return a value task, and then the signature is the same. We get a function that gets in essentially the input, right, T1, as well as the state. And then what we can leverage with C#9, we now have support for static lambdas. And with static lambdas, we can essentially enforce that there is no ability, compiler enforce, there's no ability to access state that is outside the lambda. And that's just essentially almost like a syntactic sugar, right, that we put in place. But then the compiler makes sure we cannot access anything outside. And then what we do is we also leverage value tuples and value tuple deconstruction that has been introduced with the newer runtime and C# features. So what we can do is we essentially pass the operation itself plus the state as a value tuple into the method that then gets passed into essentially the function delegate, and then we deconstruct it. So we extract the T1 again and the operation, and then we execute the operation that we extracted, including the state value. Sounds a little bit mad scientist stuffy, like I realize. But with that, we can then essentially get rid of all the closure allocations and all the function delegate allocations. And if we decompile the code, we can then see that everything is now statically cached. And you see that usually when you look at the decompiled code, that where you have like stuff like static fields that are compiler generated, that are lazy assigned once the code is executed. And with that really small change from the code perspective in that helper function and the functions that build upon that helper function, we got rid of the display class allocation, the function delegate allocation, and we can also support value task-based methods to adhere to the designed guidelines of value task returning methods. And to demonstrate, and I'm coming to some of the other questions soon, but to demonstrate how important that is, I want to give you, outside of the Azure SDK, a quick real-world scenarios of I have been applying some of these optimizations of getting rid of closure and display class allocations in recent iterations on AnswerWith Bus, which is basically a messaging abstraction library inside what we call the pipeline and the pipeline execution. And this is how it looked like. So after we got rid of the closure allocations and display allocations, we essentially got 78 to 79% speed improvement, right? Which is like 4 times faster, right? And all the allocations are gone. Let me go back. As you can see, it's like depending on the pipeline depth, on the depth of the code and the number of executions, you basically get down from whooping 20 megabytes of allocations down to just nothing, right? And we are also way faster. So really, as you can see, even though some people are saying, well, it's esoteric to do closure allocation reductions, if code is executed at scale, doing tiny changes like that has a massive impact on how the code is going to behave in production at scale. So the question from Sergio, I think it's more of a question that is related. He asked a question about what's the suggested approach to value task, and is it correct to use them per default instead of task? I will answer those questions at the end because it's a little bit derailing the talk. I hope you forgive me, Sergio. But hold me up on it, we can have that discussion. But how would you actually detect these allocations? So what I usually do is I use memory profilers and I watch out for excessive allocations of the display class or variations of action and function delegate allocations. That's one way to do it. But there is also a more proactive way that you can do while you're writing the code. So for example, if you're using Rider, you can use the heap allocation viewer, or if you're using Visual Studio, you can use the heap allocation analyzer, which is a Roslyn analyzer in Visual Studio that actually hints you at closure allocations in your code while you're writing the code, which is really handy. Then what's also happening is in the .NET runtime, there are more and more types that currently support delegate-based stuff, right? And those types, they're actually getting extended with delegates that accept a state parameter. And once you have these delegates in place, you can start passing the state into those delegates, and then you also get rid of closure allocation. So watch out for these changes in the .NET types. And one example I'm bringing it to you here is, for example, the concurrent dictionary. So the concurrent dictionary has undergone some changes, and it has a new API addition that on the get or add method as an example, where you can essentially pass in, where you're not just getting the key, but also the state. And the good thing is it's also a generic, so it's basically typed. So what you can do is, for example, you can apply the same trick that as I did in the previous example when you're using the concurrent dictionary. You then pass a value tuple of your multiple states into the dictionary, and then you mark the delegate as static, so you cannot access anything that is outside of the delegate. Then you deconstruct the tuple and you have access to your state, and then you have no closure allocations anymore. So that's a very easy optimization that you can do that gives you good benefits, as I have shown before. Cool. Then the next one is JavaScript inspired. Yeah, I have to trust you on that one. So the next one is pool and reuse buffers, and of course large objects. I'm bringing you an example here of the Azure Service Bus SDK. So the Azure Service Bus SDK has this concept of lock tokens that we talked about. Like I said, it's a glorified GUID. And under certain type of modes, it essentially gets byte streams from the network with these lock tokens in it. There's a byte arrays, byte streams, and it needs to turn them into its GUID representation. And what the SDK had there, it had this array segment creation, and then that's the most important piece here that we have to look at. It had this GUID buffer. It created a new byte array of size 16, and then it used buffer block copy to essentially copy the data that is coming from that array segment from the network into the GUID buffer, and then creating the GUID with that buffer. And because this code is executed on the scale hundreds and thousands of times, these are unnecessary allocations, both from a perspective of 16-byte array allocations as well as the buffer block copy. And well, my first naive approach was, well, I knew that there is this thing called array pool. It's a way that it's a class that allows you to rent arrays, and it manages blocks, so chunks of memory, and you can rent a chunk of memory, and then you can use it. And once you're done, you can return it. And that's what I did. Is I went ahead and I rented the 16-byte size array from the array pool, and then once I was done, I returned it back to that array pool. And I was like, yeah, cool. Now I have optimized this piece of code. I'm no longer allocating a byte array of 16. But of course, because we have to be persistent, we have to actually understand whether the changes that we did actually benefit us anything. We have to measure it, right? Fire up, again, our favorite benchmarking tool, benchmarking.net. And this is how it looked like. So what happened is essentially we have saved allocations. So we got rid of whooping 40 bytes of allocation, but we are essentially 226% slower. Well, it might be that for some cases, again, context is key. This is okay because we desperately want to save allocations because we are so memory constrained and we want to make sure that the GC never kicks off. And we are willing to pay the price of slower execution. That might be a trade-off that we can make. But in this specific case, we can actually do better, much better. And what we can do is with the introduction of span of t, and the keyword is called stack alloc, we can now directly allocate memory on the stack of the method. And because it's a very small array, and I'm going to talk a bit more about that stuff later, we can just do stack alloc of byte 16. And then we have that on the stack of the method. When the method returns, that array is automatically cleaned up with the memory of that method. There's nothing we have to do, and it's actually not a heap allocation. Again, it's on the stack. And then what we can do is, instead of buffer block copying and stuff like that, we use the span based stuff. So we turn essentially the array segment into a span, and then we use the copy to method on the span to directly copy the stuff into the stack allocated memory. And that, if you measure it, that gives us now really interesting performance characteristics. So when we look at this, we also got rid of the allocations like before. So from that perspective, we haven't achieved anything. But then we're actually now 45% faster than the original version. So we have made things quite significantly better. By the way, you have to be very careful with stack allocations, because you should not allocate more than the stack actually has. There are some guidance around. It's still a bit premature, the guidance from the .NET team. I'm going to talk a little bit about the fluffiness of this part in the later section of the talk. And in some areas, you might also, if the stack allocated array gets bigger and bigger, you need to think about local initialization. I'm going to talk about that as well, but I just want to hint it at you. Cool. And then one of the things that is also a super easy win is pay close attention to parameter overloads and boxing of parameters. There are actually many methods, if you look at it from a framework perspective as well, and sometimes also open source projects that accept the params of object array. And that can lead to very sneaky and costly array allocations all over the place that you might not even be aware of. And with the newer incarnations of the .NET, there have been a number of improvements that have been done. And because they looked at telemetry data, and then they saw some APIs are always being used in certain ways, and they optimized those APIs for how they were used by their users. And one example is task when any. Right, so task when any, the original method, it had a params of task array. So that, but many users were actually calling it always with await task when any, new task array of 2 tasks, right? And because they had telemetry, they knew that, and they introduced a new overload that looks like this. It essentially has task 1 and task 2. And then once you use that, you get rid of your array allocation. Big win already, but with a very simple change. And similarly, also, for example, with cancellation token sources, that's also something that gets used quite often, right? When you, for example, create linked token sources, it was always a params array. They have realized most of the time you always want to connect 2 tokens. Now they have introduced a new method overload that accepts 2 tokens. And that's it. Now you get array, get rid of the array allocation. And that's pretty cool. Good. Are there any questions at this stage? No? Thanks, Jose. Thanks, Jose. Cool. Let's go to the last one, the last area. It's you should be avoiding unnecessary copying of memory. So the key aspect, how you can avoid copying of memory, is span. So with the introduction of, I think it was around C# 7.3, they introduced span of T and memory of T. And essentially what it is It's just a representation of a continuous region of arbitrary memory, right? It can be native memory, it can be managed memory, whatever. But it just essentially is more or less a pointer to a memory and a length. That's a span, right? And span is essentially a value type that points to something that is on the stack. And then there is the memory of T, and that is just its heap variant. And that's the main differentiator, because what it means is spans, you cannot, for example, pass spans to methods that return a task, because how the state machine works and everything, there will be state copied around, which means methods will essentially return, right? Which means the stack will go away, and therefore you cannot carry over state that is represented as a span. So then for those cases where you have like, for example, async methods, you always need to use the cousin of span, which is memory of T. But what are good general rules that we can apply to avoid unnecessary copying of memory? And let me ask Boris.
Give them to me!
So let me present to you a few things that I have extracted from my learning experience with the Azure .NET SDK. So one of the things that I usually look out is I watch out for immutable and read-only data that is copied around. Sounds super silly, but you would actually be surprised how many times it happens, right? By definition, if you have memory that is read-only, why should you copy it? Just get rid of it, right? Then you should look around for stream and byte array usages that are copied or manipulated without using span memory. And I also try where I can to replace existing data manipulation techniques or methods with newer span or memory-based variants that are slowly being introduced into various incarnations of the .NET or runtime. There was a comment from Stefan. Stefan said, also structured logging uses parameter object. You may use logger message define. Absolutely, yeah. And there is also, in the README, there is also another thing that most people forget. For example, if you're writing custom event sources also have a params-based overload. There's also ways how you can use stack alloc and structs to essentially allocate a struct on the stack and then pass that by ref to the event sourcing methods. There are various ways how you can get rid of those params object, and they usually pay out again if code is executed under scale. So be aware of those. Cool. So watch out for immutable and read-only data that is copied. Well, here is an example again from the Azure Service Bus SDK. So they had essentially a helper method that allowed to create an outgoing message, that's the service bus message, from an incoming message, that's the service bus received message. And this is how the code looked like. It took the body, it created a byte array of the length of the original body. Then it did an array copy into that cloned body, and then it assigned the cloned body. And as it turns out, the service bus received message has a binary data that the body is represented of, and internally it's a read-only memory of bytes. And that is a non-pooled array that is materialized, and it's read-only. You cannot change it. Right? So why would you want to copy it? So the simple change there is basically just assign the original body to the copied message, allow it to be sent. And I mean, this improvement is huge, right? Every time you call this method, it was like a huge byte allocation, a lot of CPU cycles wasted for no added value, right? In other times, it's a bit more tricky to actually diagnose and optimize copying stuff, and it requires deep understanding of what is happening under the hood, for example, in the framework and library that you are using. And let me give you a few examples about this. So, for example, in the Event Hubs SDK, there was a new publisher type that was introduced. that used a partitioning hash function that essentially turns strings into partition code hashes. And that part was used 30 to 40% on the hot path from all the Event Hub client SDK usages. And it therefore represented a non-trivial amount of CPU and memory cycles that were wasted for these publisher types. And the hashcode function, it looked something like this. So this is this generate hashcode function, and it has, it looks pretty innocent, right? We have like, what is it, 2 lines of code. So we get the encoding, we call the compute hash function, and then we have encoding get bytes. And that's it. And then we have some algorithm there. And what we can spot there, if we zoom in, is we see there is a byte array passed to that method. And if we zoom out again, the byte array is actually created by the method encoding.getBytes. And because it returns a byte array, there's a strong indication that it's not managed by any pooling because we're not returning anything, right? Therefore, it's probably a copy and it's an allocation of a byte array. And the most important part is it is essentially bound to the input, right? And because we're getting input from the outside, it's a very short string, but it can also be it's a very long string, right? So that means the longer the string it gets, the more bytes we allocate, and then the slower this method actually gets because we are executing many more garbage collection cycles to actually clean up the chunk that we allocated when this method got executed. But as I said, in this specific piece of the code, it's not enough to just say, oh, it's get bytes. It potentially does something dangerous, right? You actually have to go read up the method definition of get bytes and to understand what it does and how it behaves, and sometimes even go deeper to essentially look into the .NET sources to understand what it's doing if the documentation is not good enough. So that requires some non-trivial amount of effort. But let me show you how the principles that we have been discussing applied would look like. So this is the optimized method. And I'm going to zoom into various parts of this optimized method. So what we're doing essentially now is we apply all those principles. So the first one is we're getting a string as an input. So the first thing we do is we turn it into a span representation. And then once we have the span, we can pass that to various methods that accept the span, and that's already great. So, and then the next thing that we do is, well, usually we have a string, and in order to know how much memory we need to allocate, we need to know the length of the string, right? Because, and in the bytes, Unicode bytes. So, and we can do that, and the simplest way is to do just call get byte count. The problem is if we call get byte count, again, if you read the documentation, you will find out that get byte count essentially has to walk through the length of the string. So its computational overhead is essentially O of n, right? Where n is the number or the number of bytes that are in that string. But because we're going to apply the trick of pooling memory that we learned before, we can essentially go and say, you know what? Maybe in some cases it's totally okay to just over allocate, right? Because we will be using span and slicing and dicing stuff. So let's just get an approximation of how long this string is. And if you use get max byte count, it's actually O of n. We then essentially just get a more or less rough number of how long that string is. And that's already a very good optimization. And then we combine essentially what we learned from previously, the technique of stack allocating or renting. So what we do is we look at how long is that string, and is it below a certain threshold? If it's below a certain threshold where we know that we are safe to allocate on the stack, and I'm using here 256 bytes, And by the way, that's an arbitrary number. Mileage may vary, and sometimes even in the .NET framework, it's a bit different. And the .NET team has recently raised an issue that will essentially write more guidance on how what you should be using in various scenarios. But the most important point is don't use more than the stack actually has, because that will lead to runtime problems. So I picked here 256. So what I'm doing is I'm stack allocating 256, and I'm always stack allocating that, right? I never do, if the string is smaller, let's say 16 bytes, I do not care about allocating memory that represents 16 bytes, because it's not going to give us any wins. And I will talk a little bit about that as well, with one missing piece that I'm not talking about here. And then if it's bigger than that, what we're going to do is we are using the array pool to actually get a buffer from the managed pool to say, hey, give me a buffer that can fit the byte length that we need, right? And we will not be getting exactly that byte length. We might get something that is much bigger, right? But that's not our concern, because then the next thing what we do is we will essentially go and say, hey, okay, how many bytes we call get bytes, and we pass the span there, and we pass that buffer that is either stack allocated or coming from the pool. We pass it to the get bytes method, and then what we get back is how many bytes it actually has written into that buffer. So regardless how long it is, this method returns, I wrote 5 bytes, 60 bytes, 256, right? And then what we do is we slice that memory. So in slicing just means we basically create a view over this memory to say, oh, we know the buffer is 256, but we only wrote 16. So let's narrow it down, slice it to 16 bytes, right? And then we have the slice buffer, and then we pass that slice buffer to the compute hash method. And in cases where we actually got something from the array pool, we then have to return it back to the array pool. And we deliberately not clearing this array because partition keys are not sensitive data. So we can just give it back to the pool. So that means is inside the pool, the byte array will still be having bytes that represent that string in there, but that's totally okay, because the next time these bytes will be overwritten, and we don't care about the fact that they're still there. And effectively, we care that we do not want to clear it, because that would be additional overhead that we would be paying. And we're also not doing a finally, as you can potentially notice, because we look at the code and try to understand what are the failure scenarios that can happen in this code. Do we have failure scenarios where get bytes would throw? And the triage that we did on the pull request was we couldn't come up with a scenario where we think this code will throw. Therefore, a finally is not required. And hopefully it turns out to be true. But again, you have to understand the context of the code. Okay. And once we have done that, then, sorry, Stefan said, I'm afraid I didn't understand the array copying part. Byte array is still a reference type and copied by reference. Not sure what part is copied to the method. Okay, I'm not sure I fully understand the question. Okay, from the slide before. Okay, let me just go back here, this one. When I talk about the copying, okay. Let me just. So essentially here, before this, the copying stuff was in there. The compute hash method. Okay, I'm sorry. The compute hash method. This one? Okay, so you did not understand the copying part. Okay, so on line 7, what happens there is if you call get bytes, what's going to happen is it takes the string, and internally what it does, it basically does new byte array, right? and then it creates a byte array that represents all the byte of that string. So every time you call get bytes, it does new byte array, and then it takes the Unicode bytes and it copies the Unicode bytes of the string. It copies that into that byte array that it's just allocated on the heap, and it returns you that. So that is the array copying that is happening. Okay, Stefan, I think he got it now. Thank you very much for asking that question. So apparently I did not a good enough job to explain this. It's a very good feedback. Thank you. Tommy has to leave. We're almost done. So let me just go back here. And the final change that we need to do is we need to just change the compute hash method to no longer accept a byte array, but just a read-only span of bytes. And because it's a method that returns void, and it's not an ASIC method, we can actually pass on the span because we're still within the same stack of the surrounding method. And then we can just pass it on. We could also pass it by ref. It doesn't really make a big difference. But then that's all the optimizations that we can apply, basically apply to this method based on the best practice that I have shown to you. So, well, it's not entirely true. I forgot one little thing. It's like I previously mentioned, we're going to allocate always the maximum stack limit. So with recent iterations of the runtime, there has, and the compiler, there's now a new attribute, and it's on the top of this method on line 1. It's called skip locals init. So essentially what we can do is, one of the expensive things when we stack allocate larger byte arrays, for example, on the stack, is that it will essentially make sure that this memory is cleared. So it's all zeroed out, and that is expensive. But we can tell the compiler by saying skip locals init to not emit on the IL code level the skip locals init. And then what it means is it will not be cleared. So what it means is we get arbitrary memory that potentially has stuff in there from previous executions and whatnot, but we do not really care. It's safe because we know exactly what we're going to write into it, how long we're going to write it, and then we slice it to just that memory that is under our control. So all the garbage that might be in there, we don't care, right? And that's another optimization we can do. And then stack allocating the max stack limit is actually faster than trying to accommodate to various lengths and then stack allocating various lengths. Let's do some benchmarks. For various sizes of strings, we got actually rid of all the allocations, and we are 38 to 47% faster than before. And again, this code is executed on 30 to 40% of the Event Hub's SDK client usages to actually calculate per partition, to compute hashes for partition keys, which is a tremendous saving that basically impacts all the customers that are going to use the Event Hub's SDK and that specific publisher type that I explained about. Good. In summary, these are the rules. I have it here on the slides. I'm not going to read through them again. I think that would be a waste of time. I have them here on the slide for your reference so that you can take a screenshot later or whatever. These are the rules, the best practices that I have presented to you tonight in this talk. And in case I haven't blown your mind yet with this topic, I wanted to give you a little quiz at the end to just also to see if you actually paid attention to things. So in case you're up for a challenge, the original compute hash method of the SDK, it had a bug. Did you spot it? And hint, basically, if you're lazy, the solution is in my GitHub repository that I'm going to share. But But if you're up for a challenge and you want to like think through this piece of code and learn something, think about what could be wrong in the compute hash method, and we can also talk about it offline a bit later. You can send me the solution if you want to our Twitter at Daniel Marbach or daniel.marbach@openplace.net if you're interested. And in closing, I want to say that hopefully, as I have shown you successfully, sometimes, or like most of the time, implementation details matter, like David Fowler said. It's important to understand what are the assumptions of the code base, how is it going to be executed? Is it going to be executed just once a day or thousands and thousands of times per second? How does it behave in terms of memory and allocations and performance and throughput? And then sometimes, depending on the context of the code, it also means completely ignoring all the performance lessons and optimizations you have learned today in my talks, in the areas where it doesn't matter. In the areas where it matters, then consistently apply some of these techniques, and then you get, as I have shown you, a tremendous amount of benefit from it. And I wish you happy coding and happy performance optimizations. And if you're interested in the content of this talk, in all of the code samples, the benchmarks that I've been running, you can go to github.com/danielmarbach/performance tricks Azure SDK that also contains a PDF of the slides and everything that I have shown you. Cool. That's it from my side.
Cool. Thank you very much. Gentlemen, if anybody wants to make a question, now is the moment.
Let me just drink something.
Nigel, you have a question? Okay.
I was just clapping.
Oh, nice.
Excellent talk. I mean, really fantastic.
Thanks. And thanks, Sergio, as well for the feedback. If you have any feedback that you want to share with me, I would. We're still streaming, right?
Yeah. I will.
We can also do it offline then.
Yes, we do that. So, any questions regarding to the session? Say them now. Otherwise, I will stop the streaming, and then we invite you to stay after, and then you can make these questions that probably you don't dare do when we are streaming.
I think I still have the question open from Sergio about what's the suggested approach to value task? Is it correct to use them per default instead of task? There is actually an excellent blog post of Stephen Taub about it, where value task makes sense and where it doesn't make sense. I will share it in the meetup group, because that's essentially gives a very good picture, and a very detailed picture of when you should be using it. I know that there are people like Mark Ravel in the industry that say you should be defaulting to value task. I think mileage may vary. I usually try to stick to the general recommendation to think about, is the method that I'm designing, is it in the majority of cases going to complete synchronously? Then I return value task. And if it's not, if it's in the majority of the cases, if it's doing IO bound operations like all the time, like DB calls all the time, for example, then I return task. That's my way of seeing it. But the nuances are potentially much deeper, and that blog post actually covers all those nuances. So I'm going to share it.
I think Stephen is against this option.
Can you hear me? I had super much trouble with my setup. I changed my battery from my laptop. And
we hear you.
And my headset is not working, which is, I don't know how Windows is handling things. Anyway, yeah, I guess it really depends. Oh wait, my camera's not on. I'm very sorry, I'm a bit late to the party. So
no problems.
Really, but anyway, that was amazing talk. And I also played around with span, seg, alloc, and all the stuff, and it's really fun to play with. And just watch benchmark.net giving you these magic, cool, smaller numbers. Yeah, the problem with value task in comparison to task is that the value task, the underlying source is shared. So you have a pool of value task sources, and you can run into trouble. Basically, just imagine you await your task a second time.
Yes,
this is not very common, but in theory, it should it should throw an invalid operation exception. But you could also await a different task, and for sure, you do not want to do this. And with the shared instance, of course, you should also not, when your task is completed, you should not call result. You should not call get await or get result, something like that. This can be dangerous. Where I would advise is hot path optimization. That's what it was meant for sure. There you should use it. You should also benchmark before you just throw in some value task.
Absolutely, yeah.
And maybe as you explained it very nicely, Daniel, when you have an API which is most likely synchronous, just take it. Or you design interfaces and you're not sure if your consumers might have a total synchronous path, like you have a repository, and your repository can for sure be an in-memory list. You do not need this overhead of a task object. There, I would advise take value task. It's totally fine.
And it's a great input. And I mean, value task pooling is something that in certain areas has also been opt-in, but it's coming more and more. But like with all these things, and I think async await is already quite complex, and task-based APIs, there are a lot of rules. But fortunately, over the years, the tooling has been improved, right? And I also expect this to be the case with more like analyzers and stuff for value tasks that will essentially ship with Roslyn. So that should also make the situation better, so that you have to worry less and less about the details of value task. But it's an excellent. I'm not contradicting what you said. I'm just adding something to it. That's.
I guess if you're well aware of the implications value tasks can bring with, it's fine to use.
Yeah, but it's like I tried to say in this talk as well. It's also with some of these esoteric optimizations, right? It's you have to make trade-offs. Is it really worth it? Do you really want to trump readability? And then look at the context of the piece and come to conclusion how far you want to go based on the context. And the same applies for valid task versus task and stuff like that as well. Yep. But it's a whole area of learning and experience that we have to gain. And in the majority of the line of business applications, it doesn't matter. It's not important. Any other questions? Cool.
Maybe not directly related to the string part you discussed in your talk, but did you ever also play around with the collection marshalling, so you can have a list as a span, which can also significantly improve if you work on lists, basically, at least the real list implementation, not ILIS, because ILIS doesn't give you the guarantee of having a contagious memory. So list does that, ILIS doesn't do that. And I don't know if you ever work with lists there. It's also big.
No, I have not worked with these APIs. The crazy things that I have done is essentially using the new memory marshal APIs to directly essentially go into arrays to put stuff in, to read stuff from arrays and put stuff into arrays, avoiding all the bounce checks. That's what I have done in one of the optimizations I did for the N-Service Bus pipeline. That gave some really interesting improvements executed at scale, but I have not worked with these APIs yet. No, the other ones that you mentioned, no. But thanks for the hint. Another evening gone by.
Yeah, but it was really interesting on my side, as it was mentioned as well to Oli. I also learned a lot today. Thanks, Daniel.
Thanks.
All right. If nobody has any other question, or suggestion, or prove me wrong, this kind of things, I will stop the live.